Hello everyone, welcome to the 21st Flowchat Special Edition. Today the event will be held in English and our speakers will discuss about flow assurance challenges, CO2-Rich fluids in CCS applications. My name is Maria and I'm part of the board of directors of the SPA Brazil Flow Assurance Technical Committee. First, I would like to invite those who are not member of our community yet and has interest in becoming part of our flow assurance community to point your cell phone camera on the QR code that is being presented in the screen to join our community. You may also contact us through the email that is being displayed in your screen, comunidade@flowassurancebrasil.com. Our objective is to disseminate knowledge and accumulated experience in the area of flow assurance through the promotion of lectures, courses, events, publications, seminars, and other means of scientific and technological communication. Our product, called Flow Assurance Network, is already available in our website. Our goal is to promote the expertise of research groups and companies in the flow assurance area. If you want to be part of the Flow Assurance Network, please contact us. If you are facing issues during the multi-phase flow in your field, access our website to find a research group or company to help you out. Point your cell phone camera in the QR code that's being shown in your screen or access our website flowassurancebrasil.com to access all the research groups and companies that are part of our flow assurance network. This is our last Flowchat edition of this year. We have successfully organized 7 Flowchats throughout this year. We have discussed and engaged many flow assurance related subjects. Thank you all for participating and supporting the events that are organized by the SPA Brazil Flow Assurance Technical Committee, and the Brazilian Flow Assurance Community. I would like to invite to the stand our chairperson, João Carneiro. João Carneiro holds a bachelor's and master's degree in mechanical engineering from PUC-Rio. He earned his doctorate from TU Munich, Germany, and completed his postdoctoral research at PUC-Rio. With 15 years of experience in executing and managing R&D projects and consultants, he has expertise in the development of commercial multi-phase flow simulators and flow assurance. He served as the technical leader of Sintef in Brazil for 7 years and is currently the chief science and research director of ISDB Flowtech, formerly Sintef Brazil. He is the founder and managing director of Hybrid AI, a startup focused on artificial intelligence solutions for the energy industry. Additionally, he is the co-chair of the Flow Assurance Technical Committee and the sponsorship director of SPA Brazil. Welcome, João.
Thank you, Maria, for the kind introduction. Before we proceed, I would like to make an announcement on behalf of the Flow Assurance Technical Committee of the SPA Brazil section. Following the huge success of the first SPA Brazil Flow Assurance Technology Congress in 2022, where we had the immense pleasure to receive more than 230 participants from 20 different countries. We had 13 sponsoring companies, and over 100 abstracts and high-level technical presentations delivered during the 3 days event. We are happy to announce that the next edition of FATC will take place in November 2024 in Rio de Janeiro. So stay tuned for more details, which will be discussed soon through SP Brazil's social media channels and also the FATC website. If you'd like to contribute by taking part in the technical and organization committees of FATC, you are, of course, welcome. So please take contact with us. And also, if you'd like to hear about sponsorship opportunities, to the FATC 2024, please take contact directly with me as well. So back to today's flow chat. It's a great pleasure and honor to moderate today's flow chat, which will be about CO2-rich flows in CCUS applications, and in particular, how the flow assurance expertise and the flow assurance technologies from the upstream energy sector can be used to support CCUS projects. So I have the great honor to have Dr. Eduardo Luna Ortiz from CCS and Dr. Handy Rodriguez from Woods with us. We will begin with Eduardo's presentation, followed by Handy's presentation, and after that, we'll have a Q&A session. So please use the YouTube chat to post your comments and questions during Eduardo's and Handy's presentations, and after that, it will be directed to the speakers for discussions. So I'm glad to introduce Dr. Eduardo Luna Ortiz. He's the Technical and Operations Director of CCS, a consultancy based in London. Eduardo holds a Bachelor's of Science in Chemical Engineering from UNAM in Mexico and a PhD in Chemical Engineering from the University of Manchester. He later joined Imperial College London as a research associate, where he pursued the development of multi-phase flow modeling, computational CO2 thermodynamics, green hydrogen production, and numerical methods. Over the past 16 years, his involvement in the energy transition sectors includes carbon capture and storage and projects such as VNet Zero, HyNet, Porthos, Momba, Morecambe Net Zero, and Green Sand. His current interests are on the areas of industrial and society decarbonization, sustainability, and circular economy. So, welcome, Dr. Eduardo. The screen is yours.
Thank you, Joao, for the introduction and the invitation to this chat or to this seminar. So in this talk, I will try to describe two ways in which flow assurance may evolve in the context of the CCS industry. So particularly flow assurance that I think we're going to become CCS engineers. And this is because CCS, or carbon capture and storage, is going to be or is a new industry, and it's not necessarily it's going to be the same as oil and gas industry. Before I start, I would like to have also two commercials. The first one probably is going to be about the company. And as Joao says, we are a consultancy. We have offices in London, Houston, and Kuala Lumpur. We are 6.5-year-old. We are a multidisciplinary consultancy, and we only do CCS and hydrogen projects across the world. So we have worked in approximately 100 projects across the world. Some of the clients that we have, Joao mentioned Porthos, which is one project that is here in the Netherlands. We have been working with that particular project since the start, and on other ones, particularly, for example, in the US, like with Lapis. Well, and then it's a bit by myself, but I think Joao already introduced me. The second announcement is that I'm organizing next year also another a session in a conference called Petrophase 2024. Some of them might be familiar. Apparently, it's a conference basically on thermodynamics. It's an international conference on petroleum phase behavior and fouling. Next year is going to be organized in Mexico. I'm organizing a session on CCS, hydrogen renewables. So basically, it's going to be all phase behavior on CO2-rich fluids, in experimental theory, and well, we're going to accept various papers across this the energy transition topics. So if you are interested, there's going to be a call for abstracts, and the website will be open soon. And if you want some more details, you can email me to get more updates. And now to the topic. So I'm going to have two particular topics. The first one is we're going to talk about CO2 as a reacting flows. And basically, I'm going to be talking about this particular part, which is when you transport or we gather the CO2 captured for various industrial sources or from stripping CO2 from natural gas. And that CO2 is being gathered into these gathering systems via pipelines, and then it's being sent to, for example, offshore sequestration, but also can be onshore. So I'm going to talk a little bit about this particular section with the pipelines. And because there are many sources, essentially we can have not only CO2, the CO2 is never going to be pure, so it's going to have a number of impurities, and it literally can be anything. Of course, can be water, which is the product of combustion. It can be hydrogen or nitrogen. Can be hydrocarbons, NOx, SOx, or anything. It's unbelievable the amount of stuff that can be there. And those impurities, we know that even if we have impurities that are at the ppm level, so parts per million mole per level, they can change quite a lot the physical behavior of pure CO2. For example, here I have two figures, which you can find in this reference. So here to the left, I have a fluid with CO2 with a lot of impurities, and it has a little bit of tech. In this case, it has approximately 2.5 parts per million. And this tech induces here some liquid dropout at these precious temperatures, which are normally the operating pressure and temperatures in which we operate the transport systems. If we have the same cocktail but without the glycol or without the tech, then suddenly we don't have this enlargement of we don't have this liquid dropout, so it becomes or we have liquid dropout but at very low lower temperatures. And this is just the fact that we have very little glycol in the system. On the other hand, for example, we have 2% of hydrogen or 2% of other what we call non-condensable impurities. What happens with these hydrogens that is going to enlarge the phase envelope, depending of the impurity, of course. And the problem with this is that if we want to operate, depending of your pressure and temperature operating region, you might have to operate at higher pressures depending on the amount of, for example, hydrogen. So I think it's important to know that it's not just pure CO2 what you have. So you have various impurities, and every single impurity or the combinations of the impurities is going to cause different behavior to the pure CO2. But until very recently, we always assumed that whatever the fluid we had in the pipelines will be in chemical equilibrium. And what that means is that whatever we had at the inlet of the pipeline is a non-reactive mixture, or the reactions already happen. And I know, by the way, that corrosion is essentially electrochemical reactions that we know that happen, but I'm not necessarily referring to those ones. We know now that there are chemical reactions between the impurities that are in the system, but also with the CO2. And that may be a problem because it might create undesirable products, so products that they were not present in the mixture at the inlet of the pipeline, but also may increase the concentration of other impurities, which then it might trigger new reactions. This is not necessarily new. I think maybe IFE, which is a research institute in Norway, they have been working in this kind of topics for maybe 10 years, mostly from the experimental side. But to my knowledge, as far as I know, they only have focused on reactions that create strong acids. And we are preparing a manuscript regarding various chemical reactions. And for example, if we have ammonia and CO2 or ammonia and SOx, we can create some ammonium salts, ammonia and sulfuric acid, or ammonia and NOx. We can create some other salts or ammonium nitrates. NOx and water that can create strong acids like sulfuric acid and nitric acid. And of course, this is not really good news. But also we can create perhaps solid sulfur. And this is a picture of the creation of, I think, this is nitric acid. So this is a experiment carried by IFE at these conditions and with these compositions, and they created, they saw this nitric acid appearing, and of course, over time, it started corroding, well, not corroding, but eating the metal. No, so anyway, particularly these reactions with strong acids they have detected in the laboratory, so we know that they occur. So I think that chemical reactions are then, in a way, unavoidable. Unless we purify over CO2 to 100%, which might not necessarily be impossible, but it's going to be very expensive, or we take a risk-based approach, and that means that we control the quality of that CO2, the purity of that CO2 via fluid specification, and then whatever the products of those chemical reactions we manage during operations. However, I think that we need to assume that the pipeline is effectively a long tubular reactor. And that means that, and I think that's a new paradigm for the flow assurance engineer, because now we are going to have to start looking into different terms, which perhaps for a chemical engineer, they are more familiar. For example, the extent of reaction, that means that how far a reaction has proceeded. Conversion is how much products are being formed in the system. But also there are other mass transfer mechanisms, for example, diffusion, mixing, and turbulence that are going to be important, because those, depending of those mass transfer mechanisms, you can enhance the reaction. But of course, we need to know also the kinetics, but also the chemical mechanisms of the many reactions, because we will want to have most likely dozens of reactions happening simultaneously in that pipeline. I'm not the first one to come up with this. So there is a group in Germany, which they already kind of start looking into this. They simulated these chemical reactions in a long pipeline. They look mostly in the acid formation reactions, and they have what they reported is a simple hydraulic model. There's no any mass transfer mechanisms involved, so there's no diffusion or no convective mixing. They have some kinetic data, excuse me. This kinetic data is extrapolated from literature data, which is coming mostly from combustion. And these are the results that they have in terms of the products that are coming out at the outlet of that pipeline. For example, they don't have at the inlet of the pipeline, of course, nitric acid, and the outlet they have this amount of nitric acid coming out. There is a consumption of some of the impurities, for example, SO3 that is being consumed, NOx that is being consumed, and so on and so forth. So again, like this is something that they investigated from the numerical point of view, and that is fine. And then what I thought is that I'm going to take it a little bit further, because if it's actually a chemical reaction, we need to consider so many mass transfer phenomena. So then I used a relatively simple chemical reactor model, which is the references, and this is the X1 is the composition. So, first of all, so I consider that this follows the reaction, a general reaction, which is a reactant A and CO2, and it's a reversible reaction against B. The reaction shifts to the right because of the Chatelain principle, because there's a lot of CO2. So CO2 is essentially the medium, so the reaction shifts to the production of the product B. This model considers diffusion. It considers some axial dispersion, and also it considers that the system is non-isothermal, so there is heat transfer between the ambient and the reactor or the pipeline. It's a dimensionless model, this one, and there are some various key dimensionless numbers, but the main one is the Damkohler, the one that is called Damkohler number, and this number is the ratio of the residence time to the reaction time. So this means that the high values of this number indicates that the forward reaction is fast, and the low values indicate that the reaction is kinetically controlled. And because it's quite a complex model, it's simple, but at the end is quite complex. For this particular number, which is necessarily a relatively high number, it's kind of not so high, we can see, well, I can detect some unstable behavior. X1 is a conversion of the product A along the reactor. So remember, it's along the pylon, so it's a dimensionless pylon from 0 to 1. And this is the profile of that conversion, of the conversion. What I predict here is that we have actually 3 different steady states. So P1 and P2, which are the profiles. These are stable steady states, and P2, which is the unsteady stable state. Particularly for this P2, what I see is that the exit of the pylon, we're going to have oscillations, which is this is called a Hopf instability. So I have oscillations of the outlet, sort of the conversion of the outlet of the reactor, and this is just to show that once that we start getting, for example, chemical reactions, that we're going to start modeling chemical reaction, we have a lot of transport and chemical phenomena that is going to make the system even more complicated than our normal full assurance models that at the moment we're looking without any chemical reactions. Anyway, so I think unstable behavior is possible. This is not the slogan, by the way. This model is quite simple, or it's an example, because I still need a lot of kinetic data. Of course, it needs a lot of validation, particular experimental validation for the kinetics. And this is, as I said, I'm just taking into account just one reaction. So this is going to be even more complicated if we are going to consider all possible reactions. And as I said before, we can consider even dozens of reactions. Some remarks in this first topic is that the CO2 mixtures can be considered as reactive. Liquid or supercritical CO2 is going to be a reactive medium. And we can manage the reactions via specifications or by, for example, putting design filters or operationally, so we can clean to avoid fouling. And anyway, I think we still need a lot of kinetic data to assess the behavior along the pylons. And by the way, these reactions can also occur at shipping conditions. And this leads me to my second topic, and I'm going to be as quick as I can. So we know that we can transfer CO2, I said, by pylons, but the other way that we can move CO2 around is via ships. And essentially, there are 2 ways to do the shipping. One is port to port, so from one port to another one. And then the second one is port to direct injection. So we load up a ship here, and then we send it to the CO2 storage, in which we do the direct injection. We have essentially three conditions for the shipping: low pressure, medium pressure, and high or elevated pressure. And the temperature ranges from -50 degrees for the low pressure to, let's say, ambient temperatures when we talk about high pressures. And the pressures, they vary from 5 bar to more than 45 bar. And for this particular condition of the shipping, the size of that ship, the lower the pressure, the bigger is the ship, so we can load more CO2. The high pressure, we can load less CO2. And traditionally, especially there is one project, but many other projects that are looking at shipping CO2. They are looking at particularly low pressure or even medium pressure. Why? Because when we look into the cost, if we look particularly only the cost to the ship or the shipping, indeed, low and medium pressure shipping are cheaper than high pressure. However, we need to consider, I think, the full chain of cost, not just the shipping and installation. This is because we are going to allow also flexibility for the emitters and for the project operability. And this is subject to various constraints. For example, some operational constraints that the ships, the CO2 in the ships, they need to be at bubble point based on afloat composition. This is to allow fluid expansion within the container. We might need compression and heating equipment of the CO2 prior to injection if we're going to do direct injection. Well, and the direct injection, which can be via an offloading system directly to the wall or via a platform. Any shipping condition can handle pure CO2, but only elevated pressure or high pressure shipping can handle impure CO2. And here you can see that if we increase the impurities in the CO2, there's no bubble point for either low pressure or medium pressure. And if we compare shipping against pipeline, for example, there is an enthalpy difference, so it's an energy difference between the shipping and pipeline conditions, and the minimum temperature conditions that we require when we want to inject at the injection well, which is normally, let's just say, 0 degrees, particularly in the North Sea. If we want to inject into a depleted reservoir, we're going to need probably between 8 to 12 megawatts of heating per million ton of CO2 for liquid CCS, for liquid pipelines or high pressure shipping. But if we want to do the same, inject into the depleted reservoir directly, but low pressure medium shipping, we need far much more energy. But if we're going to inject into a high pressure reservoir, so this is not a depleted reservoir, but a saline aquifer, for example, it might be possible that we don't even need heating at all. So less energy is usually required to get the CO2 into a high pressure reservoir compared to a low pressure reservoir. So, but also pipelines and high pressure shipping can be a lot more flexible when handling the light ends. Like, for example, hydrogen, nitrogen, or methane, which are the major impurities we consider. Low pressure and medium pressure ships can be much bigger, as I said before, and they have lower average cost than high pressure shipping. But again, there is a cost of the capture that might be higher because we cannot be as flexible as the specification. As I said, once you need essentially pure CO2. And the cost of disposal might be higher because we need to heat more, particularly when we are going to inject into depleted reservoirs. So there's a trade-off. And actually, we might need two specifications for shipping projects. One when we are going to do a specification for liquefaction spec, which essentially is going to be the specification that we have for pipelines. And then we're going to require probably a post-liquefaction spec, which is required for medium pressure and low pressure shipping. Also, it's important to know that once that we have the liquefaction of the CO2, this creates an off-gas. And that's gas is going to be made mostly of the light ends, so nitrogen, hydrogen, methane, whatever is lighter than CO2. And this off-gas composition will vary depending on the source of the CO2. The problem also from the thermodynamic point of view is that to predict this split or this phase behavior is going to be very difficult because there's not a lot of data at low temperature for these mixtures with impurities. And from the operational point of view, from the design point of view, this off-gas must be managed at the point of liquefaction. So once that you have that gas, we need to do something with it. And this is just an example of how the two different facilities they look between low pressure or medium pressure. They look more or less the same, and the elevated pressure or high pressure. So essentially, when we have elevated or high pressure, we can get rid of the liquefaction process at port and have less heating, as I said. Moreover, I think what is my current interest is that this becomes a supply chain optimization problem. So essentially, this is a mathematical problem in which we can define the tactical and operational plan of the ship trips, the loading and unloading of the injection of the operations. It's going to become a combinatorial problem. For example, we have 4 ports and 1 injection site. So which port goes first and how to move the CO2 from port to port, perhaps. If the ships routes are fixed or not, and of course to identify what is the optimal size of the ships, the number of ships required for each route, and what is the minimum storage required at port. So it's going to be a very interesting optimization problem. And finally, my final remarks is that high pressure shipping can be a lot more flexible about light ends. Light pressure and medium pressure ships can be bigger, but have lower average cost than high pressure shipping. But again, as I said, the cost might be higher for these various reasons. And the shipping conditions should be reviewed actually in a case-by-case network, taking into consideration the full CCS chain, not only as I said, the shipping itself, but also the various emitters, the composition of this emitter, the distances from the emitters to the port to the injection site, and also the storage reservoir conditions, which might change over time. And I think that's the end of my presentation. Thank you very much.
Hello, everyone. I think João was going to come in or not? Okay.
Thanks a lot, Eduardo. Great presentation. We'll have the chance to discuss about your perspectives in the end. Now, it's my pleasure to introduce Dr. Handy Rodriguez. Handy has more than 15 years experience in R&D and design of flow assurance and oil and gas production systems. He's currently based in Houston and is a flow assurance and CO2 transport lead consultant for wood projects in the Americas region. He also works as a manager for Wood's flow assurance team in Brazil. Previously, Handy worked for 13 years at Sempes Petrobras, managing flow assurance and artificial lift R&D projects. Handy holds a PhD in petroleum engineering from the University of Tulsa and a master's and bachelor's degree in mechanical engineering from the Federal Technological University of Paraná. Handy, the screen is yours.
Okay, thank you so much, João. Thank you, FP Brazil, for inviting me for this talk. This is a very interesting topic that we're going to be talking now, and I hope I can give some insights for the flow assurance community in Brazil on how we are dealing with these CO2 transport and CCS applications. So I'm going to start off sort of giving some introduction on Wood, which is the company I'm working for. It's not very well known in Brazil, but Wood is actually a leader in consulting and engineering worldwide. It has more than 160 years. It has more than 40,000 people worldwide. We have operations in more than 60 countries, and we've been doing a lot of energy transition, lots of engineering work there. These are some of our clients through the years. Of course, I'm not going to go through each of them, but just to give the whole picture, that Wood have been working with all the major companies in oil and gas and now on energy transition. So we partner with most of them. Specifically into the flow assurance side of things, Wood has been doing a lot of flow assurance work over the years. We have our energy and flow assurance group. So we do everything from concept selection all the way to decommissioning and everything in between. We do pre-feed, we do feed, project delivery, not only on the flow assurance side, but on the subsea equipment, pipelines, and now again entering the energy transition market. Also, as I mentioned, entering the energy transition, we have been delivering solutions in every space on the energy transition, from CCS, solar, wind, hydrogen, and particularly on CCS, we have more than 150 CCS studies going on, from concept to more evolved studies. So this is all to say that Wood has been well positioned in the energy transition space. And so, but what I'm trying to do in this presentation would be to kind of bring a view on how the flow assurance engineer and how the work of the flow assurance engineers can be translated into this new job that is being created, the CCS engineer. And it involves a lot of the things we are used to do. So gonna try to show you some of that. Okay. But to start off, we have to look at CCS as a whole chain, right? It's not really economical to have one particular emitter of CO2 and one reservoir injection. So the industry has been thinking in hubs, right? So we usually have CO2 collection hubs, and we can have CO2 for as many sources as possible. This CO2 will come to these collection hubs, and then it would be transported. This transport can be made through ships or trucks or several different ways, but what we are going to deal here is transfer through pipelines, which whenever possible, it is the most economical. And of course, then we have the actual capture of this CO2, or usually through injection in reservoirs, onshore and offshore. And yeah, so I'll be focusing on the transportation part of it, okay? So the way one way we like to think about CO2 transport, and this picture kind of tells it, it's these hubs, they are most like, they look like garbage collection hubs, right? So we have all these different emitters, all these different industries that will tie into the system. And depending on their activity, the actual impurities and the actual fluids they're connecting into the hub is different, right? So it's just like garbage. So one house has more of one type, another house has another type of garbage, but in the end, everything is commingled. And not only that, but even the one specific emitter can be changing its composition over time. So the impurities I have now may not be the same I will have tomorrow, right? So we have huge fluctuations on the composition, and that's one of the main issues, as we're going to see in the next few slides. To summarize, I'll be going through some of that, but to summarize, what are the main transportation and storage challenges for the CO2 transport? So the main one, I mean, one of the main questions we have to answer is, can we repurpose existing pipelines, or do we have to build new pipelines? And that's a very hard decision to make, and it involves a lot of the studies that we as flow assurance engineers will be doing. So some of our calculations will result in the selection of what kind of system we want, right? But I try to highlight some of the key challenges here. So for flow assurance, we have basically fluid specification, as I mentioned. We will get into the thermohydraulic behavior and how to actually have a good calculation of all the parameters we need. And with that comes the lack of reliable data and accurate models to actually get the answers we need, right? We also will have some challenges on material selection, and we have to deal with fracture control in these pipelines, and also looking to well integrity. So it's not always possible to build new wells. Sometimes, we want to reuse old wells. So it all goes into, can we use existing infrastructure or not? Right? And then there are some operation and monitor challenges. In the end, we need to measure the CO2, right? The whole goal of this industry is to capture the CO2, and it has to do with measuring how much CO2 you can capture, right? So you have to measure, you also have to monitor it. Being CO2 a different fluid, there's a lot of regulations on monitoring the systems. We have to be careful about pipeline leak detection. And with that comes dispersion modeling, which is also a work we can do to assess if there is a given leak, what's the effect in terms of dispersion. Okay. So starting off, the first section is how can the flow assurance engineer become a CCS engineer? What's kind of the position and what kind of things we will be doing on this industry? Okay. First of all, let's look into the scenarios. I have a chart here that shows pressure and temperature, and this is just for CO2, right? But I'm trying to show where are we on this diagram. So we may start at low pressures and average temperatures. We're going to need to compress this CO2, so we go through a set of compressors here to pressure up. But then we're going to transport it, in this case, showing the transporting to within the dense phase. And then we're going to storage at a much higher pressure, right? So the thing is, we're going to be dealing in a wide range of pressure and temperature. So it is really hard to have an appropriate model that can perform well over this whole range, right? We will be dealing with gas phase, with dense phase, with liquid phase. So that's the challenge. But in the end, we, as flow assurance engineers, will be dealing with pipeline flow, right? Which is something we've been doing for quite some time. The main difference I would say here is, so we have mostly horizontal flow, especially on these CO2 hubs and with all this pipeline network, we're gonna have very long pipelines. So we're talking about hundreds of kilometers of pipelines. And we have well flow, but now we're looking into downward flow. We typically on oil and gas, we want to have upward flow. Now we have the other way around. But in the end, I would say the single greatest challenge for us would be the fluid specification. As Eduardo even mentioned before, and that's I'm showing here a pressure and temperature chart, but now I'm comparing different compositions. We can see that single or pure CO2 will have a straight line here, but if we start adding impurities, this phase envelope will be changing a lot. And the issue here is that even small amount of impurities will have a great impact on the phase envelope. So, I mean, we can quickly see the changes on the vapor-liquid equilibrium. So there's this wider region here, depending on the actual impurities you have. But also there are huge difference on the actual properties. That's what also affects our calculations. So think of density for an example. Like density, especially when we are in the dense phase and near the critical point, the density varies a lot. And density really can affect one thing that we want to have a good or have less uncertainty, which is the measurement. Typical measurement systems will rely on the density, right? So having an accurate density will result in having a good accountability of money, which in the end you're injecting the CO2 and getting your credits for that. We will have some effect on viscosity, which can impact, of course, the design of your compressors and the pipeline diameters. And some other parameters like speed of sound and JT cooling, Joule-Thomson cooling effect. So this will have some effects that I'll be touching later on. Another very important thing related to the composition is actually solubility of liquids. So being water or glycols or amines, you want to know what kind of concentration of water we can have so we don't have liquid dropouts, or we don't want to have liquid water in the system. So that's another area that we should be prepared to tackle. And again, I just needed to point out that we have lack of reliable data and lack of accurate models for that. So as a flow assurance engineer, again, we have to select an appropriate equation of state for that. And in many cases, this equation of state can and will be different depending on your application. So depending on the project, depending on the impurities that you expect to have, depending on what kind of analysis you want to do, you might be changing between different equations of states. We also have to be always checking updated experiments and new field data where we can go back and check those equations of states. And also keep in mind that PVT software is evolving constantly. So newer versions are always changing their basis of calculations, especially for these CCS related calculations. So we gotta be checking new versions and making our comparing to our benchmarks. Now, now going to the thermal hydraulic modeling, and coming from oil and gas, we kind of have done a lot of that. So basically, we're going to be doing fluid flow simulations, right? That's what we've been doing offshore and onshore, and we will be dealing in most cases with single phase flow if we select to have these CCS systems in either dense phase or gas phase. We mostly will be dealing in single phase flow during steady state. However, we will be running a lot of transient simulations, especially special cases like shutdowns and blowdowns. So shutdown is something that it will happen eventually when you have a running system. We cannot have 100% reliability. So every once in a while, you're going to have a shutdown. And we want to know how these fluids inside the pipeline will react to these shutdowns, right? And of course, blowdowns, the same thing. Sometimes we have to blow down a pipeline, or even it is not programmed, blow down a leak or something. We will be doing simulations on that. And the key issue for these transient simulations is the phase change. Since all these fluids are complex fluids and these phasing vapor-liquid equilibrium are more complex, the phase change can be challenging, right? But in terms of output, what we're going to be looking into this simulation is, again, pressure and temperature, which will go into pipeline design parameters. We're going to be looking into network pipe sizing. Again, we might be dealing with huge networks with different pipe connecting different emitters. So we need to do an overall integrated pipe sizing. We can go back and impose some fluid specification constraints based on the results we get. So if we do some shutdowns calculations and we see that water is an issue or glycol is an issue, we can go back and change the fluid specifications. And another important one is leak detection times. So with blowdown simulations, we can see what's the system response to a leak, right? So in the end, it's a different scale from oil and gas. We'll be dealing with much larger and longer pipes, so our simulations times will be longer. But we have kind of the same problems we've been dealing. So we have simulator versions and tuning of simulators, compositional versus compositional tracking models, or lookup tables. We're going to be looking at thermodynamic equilibrium. Can we assume that? So yeah, we're going to be doing a lot of sensitivities and checking with available field data. Another thing that always comes in a project is, are we going to flow this CO2 in the dense phase or in the gas phase, right? And that's a decision for the project, right? So there's no right answer, but there are some key points that we should look into it. First of all, flowing volumes. So again, if we're in the gas phase, densities are much lower, so we're going to have much more volume. Most likely our pipe sizes, pipe diameters will be larger. However, if we're in the dense phase, we will be operating at larger pressures, so that will impact material selection or pipe thickness, right? We also have to think about pumping versus compressing fluids. On these big networks, we will have points in the network where we have to increase pressure. There's a risk management. So if we have a blowdown, the actual mass of CO2 that is leaking would be different if you're in the gas, low pressure, or again, dense phase. There's some regulatory issues which will vary country by country. And again, there's the composition coming up. Again, depending on how much water concentration you have, we could have liquid dropout easier in the dense or the gas phase, right? And also hydrates formation. Again, it's easier to form hydrates under some conditions than others, so we have to keep this in mind as well. So with that, I kind of went through most of what are the core flow assurance issues that we're going to be tackling. Now I just wanted to bring up some of the flow assurance related issues, not exactly flow assurance, but things that we might deal as engineer as well. So the first one is we might have injection challenges into the reservoir, right? So coming from oil and gas, we are used to having the reservoir and then pressure goes down to enter the well and just flows up, right? Now we have the other way around. We're going to have a higher pressure inside the well and the reservoir at the lower pressure. We're usually going to be dealing with depleted reservoirs which have lower pressure. So one thing that we have to keep in mind is, again, JT cooling. Since CO2 has a larger Joule-Thomson coefficient, we have a potential of having cooling of these fluids as they flow through the near wellbore part of the reservoir, right? So we can have hydrate concerns inside the reservoir when we're again flowing from the well into the reservoir, pressure drops going down, temperatures going down. And again, all of the impurities will have a role on that. So again, it's important to understand how the JT cooling effect will be changing based on the impurities, right? We also need to always be mindful of the phase envelope. So depending on the pressure and the temperatures that we're gonna operate inside the well, we might have a two-phase split, and it becomes a very complex phenomena inside the well. Okay? Another issue I wanted to touch is the fracture control, right? So typically, if we look at this chart will show pressure and velocity here. If we have a leak in a pipe, a small leak, the fluid will experience a decompression wave. So based on the actual speed of sound in the fluid, this low pressure wave will be flowing through the pipe. But at the same time, the fracture will have its own propagation rate, right? So one thing we want to have is the speed of sound in the fluid higher than the actual fracture propagation rate, so that we will lower the pressure before the fracture actually propagates. This will depend, of course, on the actual impurities and, again, the fluid composition. And we may need experimental data on the actual composition of the fluid to check what is the speed of sound when you're doing a design. And we We will have issues when we have like two-phase split, and there are some challenges here. And if we have a situation where the fluid velocity, the speed of sound in the fluid becomes lower than the fracture propagation, we will see this fracture propagating. Another thing is corrosion. So we all understand that CO2 plus water it's not a good combination, right? So depending on the fluid specification, we might need to increase our capex and opex to have better pipeline design, right? So a key thing here is if we can prevent free water, that would be beneficial for the project. And again, it goes to the fluid specification and the equation of states we're using, and trying to see if the amount of water that we have from these emitters will pose a problem to the system. And the last example I'm showing here is, again, the CO2 plume dispersion modeling. This is something that we can do with CFD, which is part of our flow expertise. So whenever there's a leak, we need to know, based on the mass flow that is leaking and the position of the pipeline, we need to know how long it will take for this CO2 plume to reach high populated areas and whatnot. So we can also do a lot of CFD and even more simplified models to assess this CO2 dispersion. So to conclude my talk, I'm bringing the key takeaways. As I mentioned before, fluid specification is the key challenge for us. It can vary a lot from emitter to emitter, from project to project. And we gotta be able to correctly model these impurities in our equations of states and in our thermohydraulic simulation models in order to get accurate results for the project, right? And some of the solutions that Wood have been working on is we participate in JIPs, Joint Industry Projects, where we've been studying different equation of states and different experimental data, and we've been providing guidelines for the industry on how to deal with this, all these impurities. We have developed models to better calculate all these parameters. And we've been involved in several research or industry programs trying to better make our models better, right? On the system integrity, we're going to be looking into material selection and fracture control and web integrity. And on the operation side, again, measurement and monitoring. And one solution that would have been providing the industry is real-time monitoring. We have our systems already implemented in CCS projects, big CCS projects, where we've been doing real-time monitoring of these CO2 pipelines. With that, I end my presentation. I hope I could start this conversation on the flow assurance CCS in Brazil. I just wanted to add that Wood has been working with that in quite a few projects in Europe and US and Canada, and we will be happy to be bringing this knowledge to Brazil and have the chance to talk with all the players on this market. Again, thank you for the opportunity.
Thank you very much, Andy. Thank you, Eduardo. Great to hear the perspectives from two leading players in CCS projects. In particular, Andy is based in North America, Eduardo in Europe. So I feel it's a great opportunity for us in Brazil to have your presence here today. It's kind of a glimpse into the future, into what we expect to be seeing in Brazil soon. Brazil, and in particular Petrobras, has built a great expertise in ultra deep water sort of CCS, EOR projects for pre-salt, right? Petrobras has also extensive knowledge about Brazil's geology and also experience in building complex and large infrastructure projects. We see the first pilots already being planned in Brazil to capture CO2 from industrial sources and storing in saline aquifers, and the strategy to develop CCS hubs in the future. So before we get some questions from the audience, I will start with one myself. So when we talk about these hubs, potentially gathering CO2 via pipeline networks from different sources, right? We hear from Handy and from Eduardo, we have a large uncertainty about composition of the stream, and you know, very little quantities of impurities, as you both highlighted, may have a huge impact on the phase behavior. We saw Eduardo's perspectives on the potential chemical reactions that might occur. So my question is how to deal with those uncertainties in terms of composition of the streams when designing such systems. So can you talk a bit more about that, both of you, Handy and Eduardo?
Well, I can go first if you don't mind. So there are two key aspects there. First of all is all these hubs, they will be developed by a group of companies, right? So you have to be upfront and agree on a spec. We have to set limits for them. What's the minimum CO2 composition and what's the maximum on each impurity, right? And then following that, each of them has to comply with that. So just the first one. And second one is designing for uncertainty, right? Typically on the oil and gas, we are used to reservoir uncertainty, which is typically not the flow assurance. We are just uncertainties with those guys, right? But here is on our table. So we gotta come up with different scenarios, more critical, less critical, and sometimes even do the job twice or three times with different scenarios and try to get the limiting cases. Yeah, that's my take on it.
Right.
Yeah, I agree with that. No, but I think on the uncertainty point of view, and I think again going out that restaurant engineers are actually quite good at doing, calculating P10s, P90s, and all doing this stochastic simulation. So I think from the facilities point of view, from the operations point of view, we need to actually start looking into, doing more that kind of probabilistic design, because doing stuff like 2-3 times or 4 times, like you never know which one is going to be your worst case scenario. No, so I think the more that we progress and the more that we embrace, also other disciplines, like disciplines like in chemical engineering, modeling with uncertainty is actually quite I would say standard practice. In pharma, people design with uncertainty. So uncertainty is part of your design, and I think particularly in CCS, or at least at the beginning, at the start of the industry, I think we need to start embracing that kind of new, new for us or for the industry, but at least all these kind of novel techniques, that probably are around.
Yeah, absolutely, I agree. And then on another aspect is about, you're doing, calculations, right? So you're using simulation tools to do those calculations, right? And probably simulation tools that have been designed for oil and gas systems, right? And my question to both of you is, what is your take on the qualification of the usual simulation tools that have been traditionally used in oil and gas for CCS type of applications? And what do you see as research needs to improve the reliability of the models and the simulators to be applied in the CCS applications?
I'll go first now. So I think as long as you're in single phase flow, I think there's, it's very easy, no? Like there's no too much science about that. So I think that the main uncertainty again is going into the thermodynamics. In all, you can have the best equation state, but if there's no any PVT data, data to validate that model, then that's your first challenge. No? And I think all this experimental data of CO2 with mixture is something that has to be increased quite significantly. From the modeling point of view, I think we have all the traditional oil and gas tools for multi-phase flow, which are, I think, validated. They have been created for, I don't know, decades of research by, a lot of research done in Brazil or in other parts of the world. And, they do the work very well for oil and gas mixtures. But now we have CO2 either pure or with impurities, I think there's already, we know that they are not really good, no, for multi-phase flow. And then when we look into these transient scenarios that Andy was talking about, you're gonna have multi-phase flow, unfortunately. So we need to have that validation. He mentioned downward flow, and I think downward flow in single phase is not necessarily an issue, but the issue is when you have a multi-phase flow, which we're going to have absolutely all the time in injection wells. So that's going to be a key challenge. So so all these research needs of starting again, perhaps doing all this flow loop testing, but with new mixtures. Perhaps even building new flow loops, because maybe those flow loops are not qualified to the same type of mixtures that you want to have. So CO2 with hydrogen or other stuff. So that's going to be a real need, no? And I think, well, multi-phase flow, I think at the moment we don't design systems to run in multi-phase flow at steady state normal operations because we don't trust. Multi-phase flow, there are no flow maps for multi-phase flow for CO2 and mixture. No? So whatever the traditional oil and gas immersers they throw you, like you don't know, right? So we need to develop the new flow maps. So we need a lot of testing. No? So to answer your question, about the tools, yes, I think we can still use them to a certain extent, but once that you get into multi-phase flow, then I don't know what is uncertainty. I think also once that we start getting, the actual developments, that's when we're going to start getting also field data. It's going to be invaluable. No?
Sure. Andy, what's your take on that one?
Yeah, I agree with Eduardo, and I think the models, they were developed starting in the nuclear industry, water and air, and then they evolved to oil and gas, and now they're evolving again. Right? But as Eduardo mentioned, we always want to be on single phase flow, right? Which is not a big deal. But those transients are really important. And I would say that one difference that I'm seeing is that we already had compositional tracking models in the past, but we didn't use them very often because they weren't really needed all the time. But I think right now we need those equations of state really tied into the multi-phase model. When you're doing a blowdown and you have phase change, you got to have a very accurate thermodynamic package attached to your simulation. So I think that's the key on this development of softwares or simulators.
Yeah. So I have some questions um, from our audience here. I'm gonna read them to you. So first, Rafael Charin says great presentations. Eduardo and Handy, does the actual state of the art allow broad CCS projects implementations? A good question, it's a generic question, but what can you say about that?
Yeah, I think yes, I think yes, it allows the broad implementation. At the same time, we have discussed in this particular seminar or webinar the different challenges and uncertainties. But like also we don't have any other choice, right? We need to start this project because also having CCS is necessarily it's not an option. We need to do it, no, because it's part of the solutions that we need to apply to mitigate climate change, no. So yes, so we need to do it very carefully, but I think that current technology allows to have that broad implementation of CCS projects.
Yeah, I agree. I mean, we have several projects coming up. And every time I would say a major company gets involved, it will go after more data. It's one thing for us as like researchers trying to look for data, but when the big oil companies get into the market, they will start putting some effort on getting more data, more real field data, but I think what we have now, we can move on.
Yeah, I also agree with you. Now I have another question by Raja Gopal. Says thanks for great presentations. Then he asks any comments on variable demand, if the storage and transport may not help carbon capture. So variable demands.
Well, if I understood correctly, this is the one big challenge. Again, we have these huge networks with different emitters, and we have to agree with these emitters a given CO2 mass that they want to capture, right? And at the same time, we have to go and drill those wells. We don't know what's the exact injectivity of these wells. So you have to design pipelines that can operate in a flexible range, right? You understand that the emitter will not emit every time the same amount of CO2. And you might not inject as much as you want because the reservoir can be different from what you expect. So that goes into the uncertainty and the challenges of designing that. You gotta have flexibility.
Right. So it's a little bit about an optimization problem, Eduardo, as well, if you're designing for the shipping transport, right? So it's
exactly. So this is flexible, robust, flexible designs that you need to have, no? And again, like as I said before, as Kenny just said, no, that we need to design for uncertainties.
Yeah. So I have another question before I go back to Adriana's question. Hendy, you mentioned about the measurement systems, right? In particular about how important it is to get your fluid properties right, and in particular the density, to get the accurate flow rate measurements. My question would be if there are any developments around wet gas meters to measure water content in CO2, more close to the capturing side. Do you see any developments or in this area, or current technologies able to do the job? So accurate, water content measurements in CO2 streams.
I think that's also one of the main challenges is the metering and the monitoring of CO2. I think, and this is not necessarily my specialty, but I think monitoring and metering of CO2 of water on CO2, I think is doable. I don't know what is the limits, the limits of measurement that I don't remember now. But even metering at dense phase, for example, that's I think they are not even existing calibrated meters. No, so monitoring, metering is also a big challenge for the CCS industry, particularly in dense phase, and that is because in dense phase the properties they change quite a lot with little changes of pressure and temperature, and if you add the impurities, then it gets even worse.
Right.
Yeah, I don't have much to add on that. It's not really not my
Yeah.
expertise on the measurement side.
Right. Yeah. And then it's just I was started talking about water, and then just because Adriana Teixeira is expert on hydrates, and now she asks about. So she first says excellent presentations, both of you. She says she had no idea about the large number of contaminants that could exist in these systems. And then she asks, is water a possible contaminant? And if so, if hydrates are a problem? I think both of you have mentioned that, but if you can elaborate a bit about the problems of eventually having hydrates in the system.
Yeah, I can comment on that. So I showed an example on the well side of things. So when you're injecting to the reservoir, you can form hydrate there, and you can even plug your reservoir and reduce your injectivity. And I mean, not only hydrates, but there are so many other solids that can form when you're lowering the pressure that can plug your reservoir, right? But also on the pipeline side, we have some hydrate formation data for these kind of systems, and it's easier to form hydrates when you're in one phase. It's easier than the other, so that goes into the selection. If you want to flow in dense phase or gas phase, you gotta keep in mind that you're gonna be close to hydrate. And when we have those blowdown simulations, the temperature will drop considerably. So yeah, hydrate is one of the issues that we will see.
Okay, Eduardo, any further comments about the hydrates?
No, well, no, I think I agree with what Henry he says. Remember, I think the main problem with water is actually corrosion. So before you start getting into hydrates, I think corrosion is more critical. No, so
Yeah.
water has to be really, really. I think that's the most critical impurity probably of all your impurities. So that has to be tightly controlled and real time monitoring, and because corrosion is the main issue.
Yeah, that goes back a little bit about my question on the accurate measurements about water content in the CO2 stream, because I know it has to be strictly controlled, mainly due to corrosion. And that's why I asked if you guys know about developments around this, because people have been developing wet gas metering for some time, but specifically for CO2, I don't know. So and then another question by Adriana. Are the available thermodynamic models reliable, or do they still require validation and further development? I think both of you have mentioned, but if you can emphasize a bit more on that aspect. So
Yeah, I think every question state might have more physics than others to model particular mixture, but regardless of that, you still need to have some sort of validation and eventually to do your regression with experimental data. No. And as we both have said, like there's no really a lot of experimental data to do this kind of even the validation. No.
Yeah, I think the models per se can be reliable. The thing is, when you add impurities, we don't actually have data for like interaction between given components, right? So most of the experiment is either CO2 with methane or CO2 with hydrogen, binary mixtures. And we can all agree that you're never going to have an experiment that matches exactly what you have in your system, right? With the exact amount, So it's always going to be a challenge. We're always going to be needing more data.
Yeah, that's okay. I think we are done with the questions. I see many people are thanking both Andy and Eduardo for excellent presentations and discussions. So I don't have any further questions on my side. And so at this stage, I would like to thank you, both of you, again, Eduardo, Andy, for the availability and the excellent content that both of you brought today. And so we hope to keep in touch and bring your expertise to support CCS projects in Brazil as well.
Well, thank you so
Nice.
much. It was a pleasure to participate. I was for a long time member of the Floresians community in Brazil, and I want to keep it that way. Yeah, it was nice talking to you all, and very good presentation by Eduardo as well.
Yeah, thank you everyone, and thank you, Joao, for the invitation. And I was not part of the Floresians Brazil committee, but probably I will be from now on.
Yeah, and I hope to see you at least next November in 2024 at the FATC here in Rio. So
I will be there.
thank you so much.